Thank you all for joining us from wherever you are. Your time is genuinely appreciated. This is my privilege to introduce to our speaker, Professor Bernard Binks, a Fellow of the Royal Society of Chemists and a former lecturer of myself. From the Department of the Chemistry of the University of Hull, Professor Binks is widely recognized for reviving interest in Pickering work in the particle stabilized emulsions. Over the past 4 decades, he has pioneered applications ranging from powdered oils to dry water to stimuli responsive materials in cosmetics, in foods, pharmaceuticals, and agrochemicals. Today, Professor Binks will introduce the fundamental behavior of solid particles at the oil, water, and air liquid interfaces, trace the evolution of classic Pickering emulsions to modern materials like dry water and powdered oil and foams, explore the interplay of particles and surfactants in commercial formulations, and the creation of stimuli-responsive dispersed systems. I am confident you will come away with fresh insights that you can apply to your own formulations and materials research. Without further ado, please join me to welcome Professor Bernard Binks. Professor, the floor is yours.
Thank you, Carmen, for the kind introduction. Good afternoon, everyone. My talk is called Particles as Surfactants, Emulsions, Foams, and Novel Materials. And I did most of all of this work in the Department of Chemistry at Hull University, where I had my career. So I want to talk to you about the new area, really, where surfactants or protein molecules are replaced by small solid particles at interfaces, whether it's a foam bubble or an emulsion droplet. And why do particles want to go to an interface? Well, if we take an oil-water interface, there is an energy gain from putting a particle at the interface because it obliterates this shaded blue area of interface, which is high tension. So there's a free energy gain by losing this free oil-water interfacial area. And you can calculate the free energy to remove a particle from an interface on the equation there. It is related to the radius of the particle r and the contact angle the particle makes with the interface. So here the particle is more in water on the left, so the contact angle is less than 90 degrees. On the right, it is more than 90 degrees, and the particle is more in the oil. And this free energy to remove a particle from an interface passes through a very sharp maximum at 90 degrees contact angle. And what it means is very hydrophilic particles, bottom left, they easily come off the interface. Very hydrophobic, bottom right, easily come off the interface. But contact angles of particles in the middle region, it means the particles are irreversibly adsorbed. And so we think of these particles as surface active, and they are then able to stabilize emulsions and foams. Now, the sort of particles that we've been looking at range in size from nanometers to microns. That's the typical size range for the particles. And there've been many different chemistries. Hematite, here you see a cubic particle, or peanut-shaped particles, rod-shaped, pyramidal. Copolymer, we can make synthetic particles of polymers, here ellipsoidal. Silica is a very classic particle type. We can make it very pure or we can buy it, here spherical. And then on the bottom right, you see Janus particles. Half of it likes oil and half of it likes water. So these are really suited to sit at an oil-water interface. We've been using many of these over the years. Shape is important and so is size. And the area was first looked at many years ago, 1907, by Spencer Pickering, a British chemist, and he was interested in making new emulsions as insecticides. He worked on a fruit farm near Bedford. And he did a simple experiment. He mixed copper sulfate, an insecticide, with calcium oxide lime, and it formed a precipitate which he called basic copper sulfate. He mixed that precipitate simply with oil and he found ultra-stable emulsions, no surfactant. And he has a phrase in his paper that the particles of copper sulfate formed a pellicle around globules. We think of this now as a particle layer around droplets. But a few years earlier, Ramsden, who was a biochemistry professor at Liverpool University, was working on proteins in water, and he noted that certain proteins precipitate, and he was making bubbles in those solutions, i.e. foams, and he says that the bubble retains the protein particles obstinately. It means they stay at the interface. And he noticed that you get some grotesque shape of the globules. So we don't get spherical bubbles. It turns out you can get non-spherical bubbles in these systems. So two British scientists opened this area up. However, the area remained very dormant for many years. This work wasn't picked up. People were working with surfactants and protein molecules at the time. And then the late 70s, 1970s, there was a revival of interest. We got interested in this in the late 90s, 1998 I started this work, and the area has grown substantially in the last 25 years. So I want to take you through, firstly, a planar monolayer. We take a Petri dish, we half fill it with water, half fill it with oil, and we then add particles, here silica, directly at the planar oil-water interface. And I just want to show you what happens as we change the wetting, the contact angle of the particles. We do this by coating it with silane molecules to different extents. So pretend we're looking down on the monolayer through the oil. At low contact angle, particle more in water, the particles of silica at the interface are very aggregated, very disordered. We increase the contact angle a little bit. We can see that many of the particles now are discrete, but we still have some aggregated particles, so very disordered. And we saw that this was when particles were more in the water. And because silica is charged, the particles are repelling each other through the water phase, the bottom blue phase. However, when we make the particles much more hydrophobic, so they now prefer the oil than the water, but they're still at the interface, we now see these very ordered particle monolayers. And you can see on the right, the most hydrophobic, the particles are separated by many particle diameters. And we worked on this and we proved that this repulsion, why the particles are separated, operates through the oil phase, the yellow oil phase, and it's a different type of interaction. So bear that in mind. Hydrophilic particles fairly aggregated, hydrophobic, discrete and separated. So that's the planar interface. Now we're going to make a Pickering emulsion. We're going to fix on silica particles. Turns out that these are 3 micron diameter, equal oil-water ratio, it's octane water, fixed particle concentration. For relatively hydrophilic particles, we start them in water, we add oil, and we're just handshaken. And what we find is droplets, emulsions called Pickering emulsions, and here are the oil droplets in water. And when we look with microscopy at the surface of the oil drops, you can see the particles of silica all on the surface. However, there are gaps and some of the particles, as you can see, are also aggregated. It's a bit like what we've just seen on the planar monolayers. When we take a hydrophobic particles, we start them in oil, we shake in water, and we now make water in oil emulsions, so the opposite type. And if we look at the surface of those water drops, can you see now the silica particles beautifully separated, discrete, just as we saw them in the planar monolayers. And I compare now, the left-hand image is oil particles around an oil drop in water for the hydrophilic particles, quite close packed. The right hand is particles around a water drop in oil, the hydrophobic particles much more repulsive. But we also noticed on this water in oil emulsion these white areas where droplets of water were meeting. So I'll just blow up 3 water droplets. Can you see these white areas? They are in fact oil films. And we decided to look at the oil films. And what we saw was beautifully close packed particles. So the left-hand arrow is the oil film between neighboring water drops. You can see the particles are very close packed, like a crystal. Away from contact, the right-hand arrow, we see the particles repulsive and separated. And if we just look at the thin oil film in detail, those are the silica particles. I mean, it looks like a set of atoms, but in fact they are silica particles, 3 microns, in a very condensed crystal. So what's going on? Well, from this analysis, we established 2 stabilizing mechanisms for emulsions. The hydrophilic case, remember we make oil drops in water, and we argued that each droplet is coated by a monolayer of particles, fairly close packed, so the stability originates from a particle bilayer. And 2 droplets will not coalesce because we've got these little ball bearings on their surface. By contrast, for the water in oil case on the right, we have 2 scenarios. Firstly, away from contact with another droplet, so on the outside, if you like, of my sketch, the particles are not close packed, they are repulsive. However, this colloidal crystal, remember we saw it in an oil film, the yellow oil film, this is what we put forward as what we call a bridging particle monolayer. So in other words, the 2 droplets share their particles and they form a single particle bridge. And this actually causes droplets to aggregate, not coalesce, but what we'd say flocculate. So these were the 2 stabilizing mechanisms depending on the particle hydrophobicity. Now, a process in Pickering emulsions is that of limited coalescence. And what that means is coalescence occurs up to a certain amount and then stops. Why is that? Well, when we first make an emulsion, it doesn't matter which type, there's not enough particles around the droplets. The droplets here are yellow, the particles are blue. And the dark blue phase is the continuous phase. So there's nothing to stop those 2 yellow drops coalescing. And by doing this, they densify the particle layer, because remember, particles do not leave the interface. So that act of coalescence increases the density of interfacial particles, and this continues until eventually droplets have enough particles around them and the reverse process of coalescence does not occur. And this is what we worked on, and we call it limited coalescence. And I just show you here, as a function of time, we took a water in oil emulsion, silica particles, 5 seconds. On the left, you can see fairly small drops. They coalesce between 5 and 30 seconds, the middle image. And then after 2 minutes and up to many, many months even, we have these beautifully stable, very large water drops. If you look at the scale bar, it's centimeter-sized drops, all touching, but not coalescing, because the limited coalescence has finished. And if we take an example at long time, here now I'm going to look at 80% volume percent silicone oil, that's PDMS, in water. So it's an oil in water emulsion. And we can change the final size of the droplets. Remember, these will be oil droplets by particle concentration. So here is the mass of particles in green, low particle content top left, fairly large drops, highest particle content bottom right, the smallest drops. So put in more particles, we can reduce the droplet size. but they're all there, very stable to coalescence. Now, a feature of Pickering emulsions is that if we can vary the hydrophobicity of the particles, can we induce emulsion phase inversion? So here I take fumed silica as a very small silica particle, and by coating the particles with silane to different extents, we change their hydrophobicity. So on the right is the non-modified silica. We call it 100% silanol groups on their surface. And the far left is the most hydrophobic silica. It's only got 14% silanol groups on the surface. We make emulsions with all these different fumed silicas, and what do we see? I'll take you from the right. As we reduce the hydrophilicity from right to left, we go from stable oil in water emulsions, and suddenly the red dotted line, we phase invert to water in oil. So hydrophilic particles prefer to stabilize oil in water, hydrophobic water in oil. And we can effect this phase inversion simply with particle hydrophobicity. We take the one just before inversion, it is oil droplets in water. Here is a cryo-SEM image of the fumed silica particles around the oil droplet in water. The scale bar is 100 nanometers, so you can see these are the fumed silica particles, and I hope you can agree the packing is virtually complete. The particles of fumed silica are different shapes. You can see maybe a peanut shape and slightly different sizes, but this enhances their packing around oil droplets. And if you plot the drop diameter, the average drop diameter in these emulsions against the particle hydrophobicity, percentage silanol, it passes through a very sharp minimum around the phase inversion conditions. So you can make your smallest and more stable drops close to the phase inversion. Now, there's a second type of phase inversion. The first was called transitional. There's a second type called catastrophic. And catastrophic phase inversion is where we fix now the type of silica and we vary the oil-water ratio. So on the left of the graph, I've got pure oil. On the right is pure water, and anywhere between them is the mix oil and water. And I'm plotting the conductivity of the emulsion, which is an indicator of the type. And if I just take you through the green curves are for a particular fumed silica, 67% silanol. Fix the concentration 1 weight percent, but vary the water toluene volume ratio. If we start at low water content, the green points, the conductivity is low, and we find the emulsions are water in oil. And then suddenly at a water content of around 0.6 volume fraction, there's a huge jump in conductivity. It's a log scale on the y-axis, and we make conducting oil in water emulsions. So we see then that we can catastrophically phase invert these emulsions with respect to oil-water ratio. And this is something you can't do with surfactants. If you try this experiment with a pure surfactant, what you make is you make HIPEs, high internal phase emulsions. So in other words, you just continue to increase the volume fraction of the drops, but they do not phase invert. And I hope you can see from this figure that the position of phase inversion, i.e. the water content at inversion, depends on the particle hydrophobicity, 100% down to 20%. So a real big advantage of Pickering emulsions, because we can make both emulsion types in one and the same ternary system. All it is particles, oil and water. Now, I've talked about simple emulsions. I want to just mention briefly that we had the idea, can we make multiple emulsions, which is droplets within globules? So, for example, we have an inner water drop. Inside an oil globule, the red area, it's self-dispersed in a water phase, the shaded light blue area. And we had the idea, the inner drops, if you think about them, are water drops in oil. We would need hydrophobic particles, the green ones. The outer globule is the red in blue, is an oil in water emulsion. So we would need hydrophilic particles, and I've labelled those purple. If we use then two types of particles of different hydrophobicity, can we make multiple emulsions? And the answer is we can. We did this with silica. The mechanism, it's a two-stage process. You first make the inner droplets, in this case, top left, water in oil, and then you make those droplets disperse back into water. So what we make is a wow, water in oil in water. And here is a microscope image on the bottom left. The oil is triglyceride. It's a triglyceride rather. Can you see the inner water drops inside an oil globule itself in water? And we obviously then did it the other way around, and we made OWOs, oil in water in oil. And here, if we did this with toluene and many other oils, inner droplets are oil. They are dispersed in a large water globule, which itself is dispersed in oil. And I can say that we still have these original multiple emulsions from over 20 years now, and they just sit there. They are completely stable. That's the inner droplets and the outer globules because of particles at their respective interfaces. Now, I've talked about the oil-water interface. What I'd like to do now is switch briefly to the air-water surface. And of course, that brings up the area of foams. So our washing up liquid is a foam. It is air bubbles in water. Shampoo, it's a foam, air bubbles in water. So the left-hand sketch here is an air bubble in water. Can we make them with particles, the red beads? And we ask the question, we've just inverted emulsions. Can we invert the foam, i.e. put water dispersed in air? And we would need different particles. And what would that material look like? Nobody does it with aqueous foams, with surfactants. You never see it in textbooks or anywhere. We ask the question with particles. So the left-hand work is actually 2 years where we were making particle stabilized aqueous foams, air bubbles in water. And the photograph on the far left is with silica particles, and you can see we've made some nice, we've extruded the foam through a piping bag, and you can see we've got, it looks a bit like whipped cream, but whipped cream contains cream which has oil in it. This doesn't. This is silica particles, air and water. And we drill down and we look at the bubbles by microscopy, and you can see we have now air bubbles in water. And I hope you can see non-spherical bubbles, the ones that Ramsden talked about. Because when you put particles around a bubble, sometimes it doesn't relax to spherical geometry. The particles jam the interface and you get these weird shapes. And if we then look at those bubbles more carefully with electron microscopy, I hope you can see the two bubbles at the bottom right, one layer, the upper bubble with a layer of silica particles, the lower bubble with a layer. And the two bubbles are touching and you see the bilayer of stabilizing particles. And what we did was we then inverted that foam, but we did it now with very hydrophobic silica. So the left-hand work is partially hydrophobic silica. If we do the same mixture, water, air, and very hydrophobic silica, we made this powder. And we wondered what we'd made. It's not a foam. And we drilled down and we realized that water drops were within this powder. So we call it powdered water, or in fact, dry water. It is a powder, but within that, there are droplets of water, maybe 50 microns diameter, coated with hydrophobic silica. And I'm flowing this through a glass funnel just for you to see that it is a powder. But if you take the powder and rub it between your thumb and forefinger, you coalesce the water drops inside and you release the liquid water. So we can convert the powder to liquid water with shear. And this raised a lot of interest, and we worked with Shiseido, a cosmetic company in Japan, and they developed a cosmetic for hydrating the skin based on dry water. So that was a very potted summary of our aqueous foams with particles on the left and our powdered water work on the right. Now, the powdered water, if you look, it's water drops in air, but they were very small inside the powdered water. You can actually make these droplets bigger. So here I'm making a few millimeter size water drop dispersed in air, and we call these liquid marbles because they're coated with particles, and the particles here are actually Teflon. The photograph I'm showing is PTFE particles, very hydrophobic, and you make these liquid marbles. You can roll them and they don't coalesce. And we've been working with two groups, a group in Israel, where we've been trying to see how does a water drop, bottom left, bare water drop on a syringe pick up particles of silica. And what we've been doing is thermal levitation. We warm the silica plate, the plate containing the powdered silica, the particles levitate, and you can see on the right that the particles now start to coat the water droplet. That water droplet eventually falls off the syringe and you have a liquid marble. And then with a group in Hong Kong, we've been looking at applying an electric field because the particles of silica are charged, the liquid marbles are charged. If we put them in an electric field and raise the voltage, we've been inducing coalescence. And in this case, depending on the size of the coating particles, we can either have no coalescence, the bottom two images, or arrested coalescence, or no or complete coalescence. And we were looking at how does an electric field induce coalescence and why doesn't it always occur? We just put a dye into two adjacent liquid marbles so that we could see them. And finally, on oil-water interfaces, we've been doing reaction chemistry, we've been doing chemical reactions, i.e. catalysis, where we use the particles as both the emulsifier and a catalyst. And we've been doing, we worked on a layered system. So what we did was we took water droplets in oil, blue droplets, and they contain, for example, hydroxyl ions, water drops. We then layered them on top of other water drops which contain HCl, protons. And what we're able to do is a sort of consecutive reaction. We bring in a reactant A, it dissolves in the top red drops, it forms an intermediate B which goes on to the bottom blue drops to form a product C. And we've been doing cascade reactions because these two reagents, if they met initially, would cancel each other's effect. So we have to keep them separated in droplets. And what we're able to do is show that in a Pickering emulsion on the right, the conversion to product, which is the red bar, is very much faster than if we simply have an oil-water interface and we stir it, say in a very small vessel, which is the far left image. After 6 hours, there's hardly any product, the red bar, but in a Pickering emulsion there's a lot. So we've been working a lot with a group in China the last 10 years on catalysis. I want to move now to an area that you may have come across, and it now moves to the air-oil interface. Where do we come across that? Well, it's oil foams. Two areas that are very important industrially: lubricating oils, oils that are added to car engines, to ships engines, to airplane engines, to lubricate the working components. They bring in air a lot, and this can cause problems with bubble formation and foaming. The other, of course, is in the formation of chocolate. Chocolate is an oily material. It is cocoa butter, which is very much oily. And for example, Rowntree's, now Nestle, they take the cocoa butter, they melt it, and at high temperature, they bring in air. And on cooling, those air bubbles become coated and they form the pores in such an aerobar. So it's a solid foam by the time we eat it, but it's actually a liquid oil foam during preparation. And there's very little literature on oil foams. Remember then, this is air bubbles in oil. And so we decided we'd look at this and see why. And we took a new approach. We decided we would try to make particles from surfactants. So what did we do? We simply took a long-chain fatty acid, it's myristic acid, it's a C14 carboxyl-ended molecule, and we took HOSO, which is high oleic sunflower oil, that's our oil. And we take that because this oil is liquid right down to minus 20 degrees. So there's no way it can crystallize itself in the temperatures that we're going to look at. And HOSO contains triglycerides, which are triesters. You can see there's a glycerol part on the left and then fatty acid chains, 3 of them on the right. These are what are called triglycerides, and HOSO contains many of these C18 chain triglycerides. So the idea was, can we take myristic acid as the foaming agent, and depending on temperature and concentration, can we make crystals out of this surfactant? The answer is we can. So, for example, 8% myristic acid in sunflower oil at 22 Celsius, we had to work out the phase diagram. We found that it was crystallizing. We found these beautiful plate-like crystals of myristic acid within HOSO, the oil. So it's a binary component at the moment, simply myristic acid in sunflower oil. And these plate-like crystals, they're about length 50 microns, thickness several microns. And what they do, they interact with each other through the oil phase and they make a gel. So you actually make what's known as an oleogel. You gel the oil, which is normally liquid, with these interacting crystals. And that's very important when we come now to aerate this system. So if we fix at 22 degrees, remember at a certain concentration of myristic acid, we make particles or crystals. Here, the vessels are what we photographed at different concentrations of myristic acid at 22 Celsius. And you can't see much, but actually, if I was to tilt these vessels, myristic acid suddenly becomes a gel. So it's a fluid oil solution which becomes an oleogel. And then after aeration, and I should say we used, it doesn't say, just simply a double beater like we would whisking an egg or fresh cream. We put the double beater inside these oil mixtures and you see at certain concentrations of myristic acid a huge increase in volume because we are bringing in air bubbles and we make these aerated oils. And if I now plot the volume of that aerated phase that we've just made as a function of the concentration of the foaming agent, myristic acid, up to about 3% myristic acid, there is no foaming. Okay, let me just show you here. We don't get any bubbles going in. We can't stabilize any bubbles. And it turns out this is in the one phase region of the diagram. This is where the myristic acid is a molecular solution in oil. But above about 3.5% myristic acid, you see a huge increase in the foam volume to a plateau. And it turns out this is where the system is in two phase, and this is where crystals of myristic acid are dispersed in the oil. And what this shows very nicely is that the crystals of myristic acid, the two phase, are surface active. That means they go to the oil air surface of the bubbles, whereas the molecules in the one phase are not. So we prepared crystals of surfactant in situ and use those to stabilize our air bubbles in oil. And this is just a photograph in the graph of a typical air, a drop of the air in oil foam from such an experiment. So that's the effect of concentration at a fixed temperature. Now let's fix the concentration enough to make a gel, an oleogel, 8% myristic acid, and we'll vary the temperature that we make it at. So I call it the effect of whipping temperature. And you see that in the one phase, 22 and 30 degrees Celsius, sorry, two-phase region, sorry, 22 and 30, we can make lots of foam, the second row, but as soon as we hit 35 and 40 degrees, the oleogel becomes, the upper photographs becomes an oil solution, and we cannot stabilize any bubbles. No bubbles go in the second row of photographs. And here is the optical microscopy, a little plate of 4 images, 22 and 30 degrees. We can see the air bubbles, and I hope you can see the crystals of myristic acid on the air bubble surfaces, the two-phase region. And then at 35 and 40 degrees, I'm trying to find air bubbles, and there aren't any, because from the photograph, there's no foam formed. And here is our little sketch of what we think is happening. Air bubbles dispersed in oil, the yellow phase, and here are our crystals of myristic acid, our plates, the red materials, and we think we know how they orient to face the oil and to face the air simultaneously. So we're able to make very nice particle stabilized oil foams. Now I just want to say that we've made many different oil foams, and for many years we were simply keeping surfactant away from the mixtures. The last example, our surfactant became particles, and it was our deliberate choice. But because I've worked with companies over many years, consulting as well as receiving funding to do basic research, I realized that we needed to look at surfactant and particles in mixtures, because this is what is involved in many commercial formulations, whether it's pharmaceutical, food, oil field chemicals, cosmetics. So the question comes, what happens when we now add surfactant to our particle mixture, whether it's an oil air, an oil water interfacial system or an air water? Well, it depends on firstly, the charge. So I'm going to very briefly tell you that we've worked with another Chinese group here. In fact, Professor Sui was my PhD student in Hull and then went on to become full professor in Yangnan University near Shanghai. If we take particles of opposite charge to the surfactant, then we have scenario 1. So, for example, if we take silica particles, which for most pHs are negatively charged, then what I'm saying is we add a cationic surfactant, a positively charged surfactant. And as my sketch shows, the positive charge on the surfactant starts to interact with the negative charges on the silica particles, and we coat the particles initially with a single layer of surfactant. Now, in doing this, we are taking off the charge on the silica, we're neutralizing it. And so I'm showing below the zeta potential of the silica particles in water as we increase, in this case, CTAB. CTAB is a C16 trimethyl ammonium bromide. It's a cationic surfactant. And you can see the initial negative charge at low surfactant goes through a zero charge, the dotted line, and in fact you can make positively charged particles, because what happens, you start to make a second layer, which is now a bilayer, where the positive charge now faces the water. So we know we can change the charge of the silica, and by doing this we also change its hydrophobicity. So let's have a look at this, what happens when we make emulsions. If we just make an emulsion with silica alone, no particles, we can't really make a Pickering emulsion. The droplets coalesce because the particles are too hydrophilic. The upper row of photographs then is CTAB alone. It's a surfactant, but you need a certain concentration to make oil droplets in water. And in fact, those coalesce over 1 or 2 days. Surfactants are not very good at stabilizing emulsions, we realized after many years. The bottom row of photographs is CTAB plus silica. So we fix the silica content at 0.5%, and the variation I show is increasing concentration of the surfactant. And I hope you can see that even at 0.003 millimolar, we make a very stable Pickering emulsion, oil in water, at much lower surfactant concentrations than we needed with surfactant alone, the upper row of photographs. So we've got this synergism in this first case, oppositely charged surfactant and particles, where we use the surfactant to hydrophobize partially the silica and bring it to the interface. And my sketch is trying to show that silica in water, we start to absorb surfactant. If we mix in initially oil, we make oil drops in water with a monolayer coated, well, surfactant coats the particles with a monolayer, and those coated particles coat the droplets by a monolayer. We also then roll that out for foams. So I've put /air. If we now look at the same sketch at the bottom, but instead of oil, we bring in air, we can make air bubbles in water. In other words, aqueous foams in this surfactant particle mixture. And we move this on a little bit further. Yeah, I kept that out. So what I'd like to do is the second case. Second case. What about now if we change, we don't have opposite charge, but we have light charge. I'm conscious of time, but I'm okay. Ionic surfactant and light charge particles. So for example, we took alumina, positively charged at most pHs, and we keep with C-tab, cationic surfactant. And here then, we fix the C-tab in this case, very low concentrations, and I'm varying the concentration of particles from 10 to the minus 5 weight percent to 0.1. And you see that at very low particle content, 0.0003 weight percent, I can make a very stable oil in water Pickering emulsion. And what we showed was that if we vary the particle concentration, which is the photographs, we don't change the droplet size. So that was telling us something. Whereas if we change the surfactant concentration, the bottom left graph, we can lower the droplet size, the oil droplet size. So that was telling us something very important. Particles, we don't change the droplet size. Varying the surfactant, we do. And we formed a little phase diagram where I plot here the alumina concentration on the y-axis versus the surfactant concentration on the x-axis. Below the points, we have very unstable emulsions. Above the points, very stable. So we know the minimum amount of particles for a given amount of surfactant to make a stable emulsion. So how do these emulsions look? The first case, opposite charge particles, the particles go to the droplet interfaces or the bubble interfaces. This time they don't. So what we did was we dried some of the oil droplets, the emulsion droplets, and we looked at them with SEM. And what we found, the droplets were bare and all the particles were in the water phase. So the way that we understand these, and we now rename them oil in dispersion emulsions, the oil droplets are stabilized by a very dilute layer of surfactant, in this case positively charged C-tab. And the particles of alumina, are all in the water phase. And what we find is a very repulsive system. The particles repel each other in the water. The particles repel the surfactant at the droplet interfaces, and the surfactant repels itself around droplets. So we have this repulsive interaction going on between many species, which gives rise to the stability in these novel emulsions. And I should say they are made at very low surfactant and extremely low particle contents. So I'd like to just summarize. Particles of intermediate wettability or hydrophobicity are very well held at fluid interfaces. Emulsions can be phase inverted transitionally, and I didn't show you this, but we can change the pH if we have stimuli responsive particles. We can do this by salt concentration changes, temperature if we have temperature responsive particles, or we can invert emulsions catastrophically, and remember that's where we change the volume ratio of oil to water. I hope you can appreciate we can make particle stabilize aqueous foams and in fact particle stabilize non-aqueous or oil foams. And these particles at interfaces act as a template for new
Thank you very
materials.
much, Professor
Carmen
Binks.
mentioned we've looked
Very,
at
very
powdered oil.
interested.
I didn't have time to talk about it. I shared with you that we can make
Anybody
liquid
that
marbles.
wants
We can
to
make dry
have more
water.
information
And
about
just
any
for the
of the
benefit
research
of
that
us
Professor
present
Binks has
today,
done,
we started
or
work
any
on this
further
way
webinars
late
that we will have,
1990,
I'm gladly
90s.
will be able to answer
In
any
2002, I
questions
put a review together in
via
this
email
journal,
to
and that's
contact
been very
at
popular. We put a book
olayaconsulting.com,
together in
and I
2006
would like to
because there
thank
was
you
a huge
everybody for
area that
attending.
had been
Thank you
opened
very
up,
much.
and we
Bye
called them
bye.
colloidal particles at liquid
Okay.
interfaces. That's nearly 20 years old now. And then in 2017, I was asked to write a review, and I decided to write it on the 5 types of fluid interfaces. Let me say oil water, air water, air oil. We've actually looked at 2 immiscible oils, which I call oil, and we in fact can make water split to 2 immiscible water phases. And the question is, can we make water in water emulsions? But throughout all of this, I've tried to have an interest in the industrial side, and that's where some of the funding has come from. So I hope you found it interesting, and thank you for your attention. You're welcome.
Thank you everybody for your time, for attending.